record. We'll now hit record, which is fine because I'm going to go into new stuff anyway. All right, so that's just a simple U substitution. U substitution is nice and works if and when I have something to cancel out. If this X wasn't here, so before I do the next problem, if that X wasn't there, if I just had the integral of 9 minus X squared dx, if I set my U to 9 minus X squared, du is negative 2X dx. So divide by the negative 2X. So then I have the integral of U du over negative 2X. Now I have a U and an X. And I can't do that. Okay? If I have a U and an X, I'm kind of screwed. So there's got to be another method to be able to do this. Okay?
And that's what we're going to do today.
And that's what we're going to do today.
Is anybody allergic to nuts?
Anybody here allergic to nuts? Definitely, like, as in you can't breathe them, or? Huh? Okay, so no nuts.
Nope, no nuts.
That was why that's why he was asking. Because I'm allergic to nuts too, but I can't ingest them. Like I can breathe, like it could be around them, but I can't ingest them. So that's why I asked the question.
No,
So no nuts. Sorry, no Girl Scout cookies for you guys. Next time he'll have more Thin Mints for you.
Whoa. Just because I have 2 more boxes at home.
All right, so let's look at this one. Because this is one of those ones that I think we have an X, right? So this one's similar to the one we just did. However, if I look at this one, I have an X squared. So if I set my U to the 9 minus X squared, my du is again negative 2X dx, and then my du, it's over negative 2X. The same problem is going to end up happening. I'm going to have the square root of U, X squared times du over negative 2X. I can't cancel the X's out. So even though there's an X there, I still can't cancel it out. Okay? So this process right here is not hard to do. Okay? And it doesn't typically take you a lot of time to do that. So I'm going to show you another method to be able to do these problems. However, this right here will save you a ton of time if it works. So check that first. Okay? Always check U substitution before you do more complicated methods. All right? Because it's normally a quick and easy thing to do. Just look at it. If you know you can't do it, go on. But if you think it might be possible, try it real quick to see if it works. All right? It'll take you a minute, but it might save you a ton of time trying to do more complicated methods. All right. Copy this down.
All of it?
All of it.
Okay.
The only thing you don't really need to copy down is you don't really need those. That's just the domain of the trig functions. So trig substitution is kind of known as inverse substitution. We're kind of going backwards. So, because we're going to make the problem actually more complicated and then clean it up and then go back to the X's, because trig functions have a tendency to cancel each other out and their identities kind of work to clean things up a little bit better. So, but write those 3 rows down because we're going to need them all. I think did not. I have to redo that. And the reason why I said always make sure to look at U substitution first is, unlike some other methods, this method will work if you could do U substitution. So unlike we were talking about how like you can't really do integration by parts, if U substitution will work with integration by parts, that might not work. This will work, even if you can do U substitution. It's just going to be a lot more work. Okay? So if you instantly go to this method, you're just going to spend a lot more time working. Yes.
The A
Can be any number.
okay, so that's not like our standard.
No, that can be any number. So it's the same number here. So we're going to actually use numbers in those for the most cases. All right, everybody good?
Wait, one quick question.
Yeah.
So if it's like minus x squared, like the first expression, right?
Yep.
Would that be sine squared theta?
Yeah.
Okay.
Yeah, you're going to see it in a second when I do the problem, how that whole process goes. I just copied you back. All right, so let's go back and look at this problem again. All right, so we looked at it. We know we can't do U substitution, so I've got to use my trig substitution. This format right here, the 9 minus x squared, matches up with which one of those three?
I was talking the first one.
The first one. So I'm going to let x equal 3 sine theta. Okay? Because if I look at the square root of 9 minus x squared, that relates to the square root of a squared minus x squared, right? So a is 3 and x is x.
Will x always be x?
No. Because if I put a number in front of that, so it was 4x squared, x would have been, 4x squared would have been 2x. Or x would have been 2x in that situation. Okay. All right. Does that part make sense? Okay. I now need to find my derivative of that. So dx, what's the derivative of 3 sine theta? 3 cosine theta. D theta. All right. Are we good to that point? Okay. I'm going to apologize ahead of time because I'm not going to write a bunch of stuff down all at once because I will use every single one of these slides to do this. So we're going to just look at that part. Okay. So I have the square root of 9 minus x squared becomes 9 minus 3 sine theta squared. It's like I'm getting out my pens. And I literally, the only pen I have is a red one and it's broken. I'm sorry. All right. We're going to do this 3 sine theta squared. We're going to square. So I have 9 minus 9 sine squared theta.
Oh my God.
I'm going to pull out the 9. And that now becomes 1 minus, oh, sine, not cosine. Sine squared theta. I had one extra step in my head. What's 1 minus sine squared theta become?
cosine.
Cosine squared. So this becomes 9 cosine squared theta, which equals 3 cosine theta.
Whoa. Okay. That's now our numerator, right?
Right. Duplicate this. So my integral now this becomes 3 cosine theta. The x squared on the bottom becomes 9 sine squared theta.
And that's because our x is 3 sine theta.
Right. So we now square it. And my dx becomes 3 cosine theta d theta.
Why? Will we combine the,
Yeah, we're going to do that in the next step.
so
We're going to do some combining in a second. Questions with how I got any of those?
squares just go.
Yes. Yeah, because we did that. That got rid of my square root.
Yeah, it's just.
All right. So now this, if we clean this up, I have 3 times 3 over 9. That cancels each other out. So I have just cosine squared theta over sine squared theta d theta.
And that is
What is cosine over sine? Right. So this is the integral of cotangent squared theta d theta. Anyone know that one off the top of their head?
1 over secant squared.
No. All right. So actually, there isn't one simply for that. There is one, though, for cosecant squared theta minus 1.
Which is just cosine.
Right.
So you just put it back to cosecant.
Yeah. Well, cotangent squared theta equals cosecant squared theta minus 1. That's the one of the Pythagorean identities. Because I can do the integral of cosecant squared theta. That one is just cotangent theta minus theta plus c.
I would have gone, that's why I was like, why are you adding?
We're not done yet.
Do we have to put it back in terms of x's?
Yes.
Seems like a bad idea if you ask me.
All right. So, first step, first question, before I do, which a lot of people think is the hardest part of this process, is everybody good to this point here? So the only reason why we had to go from this to this, I don't have an interval for This one is one of those elementary integrals that's on a list in the beginning of chapter 7 that like people should know. If you don't know it, that's one of those ones just quickly throw on your index card. But again, that's one of those ones where if I put, like, if you see this on your practice test I'm going to give you, I'd write it down. If you don't see something like this in the practice test, don't worry about writing it down. I'm not going to use it. Okay? So that's where that practice test, when I give it to you, is really going to help you because it focuses down what you're going to need to put on your index card for when you look things up. Okay? All right. So now the hard part. We have to change this back to X. I'm just going to rewrite it. So currently we have cotangent theta minus theta plus C. I know that X is 3 sine theta, right? I don't have sine theta, so I can't just like replug it back in like the U substitution thing. So we're going to move over the X. I mean, over the X over 3 is sine theta.
Okay.
So let's make our right triangle. So sine is which two sides of my right triangle? Opposite over hypotenuse. I will give you a nice little hint. The side that is missing is always the square root that was in the original problem. So this side is 9 minus x squared. The square root of that.
That makes our life so much easier.
Yes. If you did the Pythagorean theorem, it gives it to you anyway. Like that's typically what you'd have to do. But it's literally always going to be the square root in your original problem. Okay, so don't sit there and waste a ton of time figuring out the missing side. Once you get the two sides from the thing, that's the third side. Now we can figure out everything else we have here. Okay, so cotangent is which two sides?
Oh.
Opposite and adjacent, and it's adjacent over opposite. So it's adjacent, which is the square root of 9 minus x squared, over opposite, which is x. Minus the arc sine of x over 3. Because if I wanted to take this and solve for theta, I would just do the arc sine.
Yeah, because we have that.
Because you already have that, so you can just do the arc sine of it.
You know,
And that's your answer. So you know how you're asking, when do you stop? These are the ones that are really tricky because like there is multiple places in this problem that you're like, I can stop here. No, keep going.
I would have stopped that. Right.
I think I-
The funny thing about this one is this problem or these types of problems are actually way easier if I make it a definite integral. Because if it's a definite integral, you don't have to go back to x.
you need to plug in a number.
So we can plug in our numbers from theta. So you don't actually have to do this extra step. So it saves you some work down there. Okay? But that's the answer for this problem. So when we're looking at it, first thing is always try use substitution. All right, at least quickly look at it, make sure you can rule out doing use substitution. Then look at the table, figure out which one of those values you're going to set to x. And that's based on whatever your square root is. These problems will always have a square root. Okay. No square root, no trig substitution. Okay, so these will always have that square root. So this makes it a little bit easier for you to recognize these type of problems. All right. Get rid of your square root and then work through your problem. It became 9 sine squared because x is 3 sine theta.
Okay.
So I plugged that in there too. You're replacing everything with theta in this. So the square root we did separately because there's just a bunch of steps with that. And then we plug that back in. I'm not saying anybody in here is going to get to there this quickly. The more of these you practice, you'll start to look at the square root and know what it's going to come to without actually doing all those steps. Or once you start writing like this down, it's like, oh, okay, that's what it's going to come out to be. So it's like you'll get a lot faster at doing this when you figure those things out. All right. Blank page.
Impossible problems. Can't do it.
All right, let's look at this one.
Could use some that work for this. Are you sure? Because we have an extra. We're almost in difference in squares.
Even that doesn't help you. The last one, I had difference of squares. It's 9 minus x squared
Why wouldn't that?
because I can't factor it. It wouldn't be, you don't need the difference of squares. You need a perfect square trinomial to get rid of your square root. Ooh. So write the problem down. Okay. Can I do your substitution? Not letting you off easy. No. Okay.
Not because I know the answer is
That is not true. As you've learned in this class, I will constantly throw problems into you that think something will happen. So you don't ever assume that. Figure out what your x is going to be. Start there. Look at the table. So x is going to be what? I'm not looking at the table. That's why.
square root plus x.
Yep. Because and it doesn't matter the direction. So it's a squared plus x squared on the thing. Remember addition, you can switch back and forth and it doesn't matter. So x squared plus a squared is the same thing. So which is the x going to be? What's the x going to be? No, what's in the next column? It tells you what x is going to be. What's x going to be?
That's why I highlighted. I know where to look. I know where to look.
No. That's the first row. The second row should not be signed. Second row is tangent. I was going to say, wait, we just did sign. I know it's not signed. So it's going to be 2 tangent theta. Why? Table. That's the one I'm using. That's what x is. Because it was a 4. What's the square root of what's 2 squared is 4. You're never going to see the problem written as like 2 squared plus x squared. That would be always written as the square root of 4 plus x squared. But you need the 2 because it's got to be in terms of a squared. Yes.
Am I on the right?
Nope, nope, it's upside down.
Is the x squared?
Yeah.
So I've done everything right so far.
I think so.
Okay, that was my question.
You haven't done your derivative yet, though. You need your
Yeah.
dx, but yeah, your square root terms right. Yes.
The derivative and then
Yes.
Multiplying by the square root.
yeah.
Or quickly be able to look up.
The derivative of tangent is.
Yes. Fine. You should either know it or quickly be able to look it up.
That's not a good word.
All right. So again, let's just look at our square root. So I have 2 tangent theta squared plus 4. So I have 4 tangent squared theta plus 4. 4 tangent squared theta plus 1. What's the trig or the identity for tangent squared theta plus 1? Secant squared. So that's secant squared theta. So that's 2 secant theta. So my integral is 1 over 2 tangent theta squared 2 secant theta. Let me write that in red. Times 2 secant theta squared theta d theta. So if I clean all this up a little bit, the 2's are going to cancel out. One of the secants are going to cancel out. I still have 1/4, so I'm going to pull out the 1/4. So I end up with a secant theta on top and a tangent squared theta on the bottom. Now look and figure out how all the little steps I skipped to get there.
Oh, okay. I understand. Those two will cancel. Out.
So when you're looking at it, that 2 cancels with that 2. That squared cancels with that secant to get rid of it. So I have 1 secant left on top.
Yeah.
That becomes the 1/4 on the front.
Yeah, because it's. Yeah. Okay.
This 2 squared is 4.
Do I have an idea?
All right. Did you see what I did? Yes. Did you see what I did?
What?
I do math on Sundays.
On Sundays, we do math. On Wednesdays, I go to hockey games and harass your team. All right, let's look at this. So now we're at the point of we need to do our integral. So as it stands, does anybody have any suggestion on where we go?
Could we turn that tangent into secant squared theta minus 1? And get a 1 back into the
That won't get a 1 back in the numerator. Hold on 1 second. I'm going to show why his won't work. So if you change the bottom,
Oh, because it's got
it's -1, right?
Yeah.
So I can't cancel
Yeah.
like that. I could, if it was the opposite direction, I could split it apart and cancel things, but not that one. What do you want to try?
And the 1 over square root of sine square root and the secant square root.
Okay. Yes. One of the great things about trig functions is everything seems to go back to sines and cosines. So let's make it go back to sines and cosines. Because when I have all these sines and cosines, maybe I can cancel some stuff out and work. And we also know that sine, the derivative of sine is cosine and vice versa. So it kind of like lends itself well to a simple U substitution. So if we change this, I have 1 over cosine theta times cosine theta, cosine squared theta over sine squared theta, d theta. So secant is that one. And the tangent squared on the bottom is that one. So then I end up with cosine theta over sine squared theta d theta. And you'd think, okay, that doesn't help me much because it doesn't look much different than what I started with, except now it's in sines and cosines.
Well, we can use some.
Right. That's really that was the goal of getting it to sines and cosines. Because now I can make u sine theta. So du is cosine theta d theta. So I now have 1 over 4, 1 over u squared du. Which is 1/4 negative 1 over u.
We can't leave it like that. Can you?
Nope. Nope, can't leave it like that.
That's all right. But we can.
All right, so step 1. We have that. Now we're going to change the u. So what was the u? So this now becomes 1 over, or negative 1 over 4 sine theta plus c.
And we still need to go back to that.
Right. But I can change this to negative 1/4 cosecant theta plus c. So I don't have the trig function on the bottom.
Oh.
Now we need to go back to our x. What was my x? So that means x over 2 equals tangent of theta. So that tangent is what over what? Yeah, in your right triangle stuff. Opposite over adjacent. So it's x over 2, and this is d squared of x squared plus 4. Remember, that's always just whatever the square root was. So what was my cosecant is what? 1 over opposite. So 1 over x.
So negative 1/4 x.
Wait. No, cosecant's not 1 over x.
Yeah, that's
Wait a second. Like, no.
fine.
It's okay. I know what you're saying. Cosecant is 1 over sine. I don't want that. Triangle. Cosecant. So sine is opposite of hypotenuse, right? So cosecant is the reverse of that. I'm like, wait a second. That's way too simple. I know that's not the answer. Over x. That makes more sense as my answer. So it's negative the square root of x squared plus 4 over 4x plus c.
Yeah, so no there for a while.
Uh-huh.
That's
Like on a horse that came in your town or something for.
I don't know. I
What
look.
was the second one?
Oh, I was gonna say Sokoto is like what? It's funny. Like I've
Some old horse came in the town, or I can't remember what.
I've asked English teachers who have been out of school for decades to tell me one thing they remember from math class, and almost every one of them remembers Sokotoa. Sine,
opposite.
opposite hypotenuse, cosine,
I can Google the horse one.
adjacent hypotenuse,
Yeah.
tangent, opposite adjacent. But it's just one of those stupid things. Yeah, because I don't remember. There's one of those stupid things that just sticks in your head. Yes. No. Just kidding. There you go. Yeah, it's just one of those stupid things that stick in your head.
Over the past few problems, we've ended up with our square root from the beginning.
Yep.
The numerator.
That's not always going to be the case.
And okay. Is that why?
No, that's not always going to be the case. Remember, I said I would tell you if the things are always going to work.
I thought
Okay.
maybe you let us see it first and then.
No. Like I told you in the first one, like the square root's always. I didn't make you go through the second right there, but it's always going to be there. So yes, if that was the way, I would have said just, it's always going to be this over this, and you're done. No, it's not that easy.
Imagine.
Okay.
I was doing great
All right, do this one.
until that happens.
Wait. X squared plus 4.
Sure. One second. Just make sure everybody's got this written down first, then I'll switch back. That's okay. The beauty of the slides, I can always go back. Everybody got it down?
Yes.
Okay. You wrote it down? This down? No, it's a new one. Similar.
Like the same.
You want us to use
Yeah, that's kind of what I'm doing.
I just said solve it.
It's just too technical.
It was this slide? Okay.
this,
These two
this and
cancel.
this, and then one of these, and only one of these cancel.
So right, yeah, but two
It's
left
just-
in the top, so I can just pull the two out.
Why would you do the two?
Because these two twos cancel, but I still have one here. I'll just pull that one
Oh,
out.
I guess you're right. Wait, put that. Right.
Bring this right.
What?
I have two twos and then they cancel out, and then I have left over, and then I can.
So take it. This. Tangent, theta, for secant theta. And don't just it isn't parts. It's because we do this.
You didn't use some. So we had the.
It's fine.
Yeah, I think so. I don't.
It does work.
Oh,
Just took me a second to make sure that it was doing right, because I'm used to seeing the other piece. So.
that's right.
You why? Why did you find that? Because secant is
1 over cosine,
one
tangent is sine.
I missed two.
sine. Cosine. No, yeah. I think
And now we can use some.
yes.
Cosine.
Remember we talked about before?
What, no, because we had something at
Not
the very
saying
end of the last one. So it's similar.
Yeah.
Oh, where I throw things out that sometimes you don't need to do a process. What was the first thing I told you to try? Right. So why are we doing trig substitution? Always try use substitution first.
I was having a good time, all right?
You're gonna set this to this. Does it matter? No. Like you could have easily done the other method, it would have come out to be the same.
You just recognize that if there's an X on top, that substitution would be viable, but if there's no X on top, can you just not do the substitution?
A lot of times, yeah.
Because if there isn't an X on top,
So, but here's what, like,
going through substitution is just a waste of time, because you know it's not gonna work.
correct. But there are some situations like that, for example. I can do use substitution with that. Okay, it's like there's some things that come up like that aren't exactly that, but in these type of problems, yeah, you probably could. If you see the square root and you don't see the X, like if it's got to be one less than what you got there, in essence.
It's exactly one left.
Yeah, because derivatives take away one.
I just want to make sure like that.
Yeah.
So if I see that, I
Yeah.
can do use of. If I don't, I can't.
Right, because this is now going to become 2x dx. And now I can do my use substitution. He did the complete use substitution in his head like that. Like I'm looking at it like I was like, he didn't. He literally did it all the way through. I'm looking at him like, wow. Every step is correct. It's like you just did it all without actually doing you. So we get the integral of x over square root of u 2x dx. Oh, sorry, not 2x dx. du over 2x. So the x's are going to cancel out. This becomes the integral of the 1/2 can come out front, u to the negative 1/2. So I get u to the 1/2 with 1/2 more out front. So 1/4 u to the 1/2, which is 1/4 the square root of x squared plus 4 plus c. So, but yeah, always look for that first. Yes.
I didn't get. I, well, I have,
Hmm?
when I took the integration of u to the -1/2, I got u to the 1/2 over.
Oh, the 2. That's I did it. I forgot to flip it. You're right. So that cancels out. So it's just that. Because it was 2 times 1/2, which is yeah. I forgot. This is why I was amazed that you actually did it all out with like without doing that. Because like even like me doing those little things, like you forget to flip something or look those little things. That was impressive. All right. But if you did this out with TrickSub, you could do it. How many more steps did it take you? Or were you
I wasn't even done.
like I think it takes a lot of steps to get through. Okay,
Good
so
practice,
always
though.
yeah, but always look for this first. All right. Look at this one.
Do sub does not work for that one, does it?
No.
But it is a definite.
Yes. I want to make sure I do one definite one so you can see how this process works because it does work slightly different at the end. No more tricks. That was the one trick of the class. No. This class period. This one's got a couple things with it. So if you remember, if you look at your original table, the options were those are the 3 options. Okay. I don't kind of have that here. So no, I have a square root cubed. So the first thing we've got to look at is I've got to look at trying to fix this so it kind of looks like one of those. Okay. So the first thing I'm going to do is I'm going to change it so that it's 4x squared plus 9 to the 3rd. That's that 3 halves. The half is the square root. The 3 is the exponent. Okay. Now it's kind of getting into that format. But I've got I got an extra number here. Remember that whole concept we had before, is x always x? No, this is the case for that. So I'm going to rewrite this again. I'm going to write it as 2x squared plus 3 squared to the 3rd. Now I have my x is 2x and my a is 3.
Why did we run it?
Because I wanted to get it to look like that.
I see. Okay.
Okay. Do you have to write it? Did you have to do that step? No. The better you are at recognizing things, you could have looked at that step right there and said, okay, it's 2x and 3
That's why.
and been done. Not everybody's going to be able to do that quickly. So sometimes it's nice to be able to write that extra thing. So that's my x and that's my 3. Or that's my a. So what's my substitution step I'm doing? It was tangent, right? So, but it's going to be 2x equals, what was that, 3 tangent theta? So x is going to be 3 over 2 tangent theta. Yes.
There's gotta be a better way of like having the x equal something. Because having
I know x equals
2x.
it's not. It's
It should
but
be like x sub the equation. I don't know.
yeah, it's
To differentiate between.
I agree. It's like it's yeah. X goes to 2x. I don't know. The big part though is to make sure you put the 2x there. So not just an x. So x is now 3 over 2 tangent theta. After this, it's the same process. With the fractions and stuff, it becomes a little messier, but let's look at my square root. We'll break out the square root part. So we've got 4x squared plus 9 to the third. And x was 3 over 2 tangent theta. So I've got 4 times 3 over 2 tangent theta squared plus 9. So I get 9 tangent squared theta plus 9.
How'd you get,
3 squared is 9.
Yeah.
2 squared is 4. 4 divided by 4 is 1. So this now ends up being 9 secant squared theta.
that's
I told you, I said the problem when you have the square roots and stuff like that is it becomes a little messier when you have the fractions and stuff. But
and that's already done.
I think that was the denominator. Yeah, that was the denominator. All right, so my original problem was this.
X cubed.
So x was 3 over 2 tangent theta. My dx is what? Yeah, secant squared theta d theta. And my 4x squared plus 9, the square root of that became, or cubed, became 27 secant to the third theta. So now here's the next piece to this. So you can do, this is where two methods diverge. And you can choose the method you wish to do. You can complete this problem as it was the other problems that we've done, leaving your interval in x's. You then just have to translate back to x's to plug in the numbers. That's method one. The other method is to use what we did, or what you should have seen in the substitution, and I've done a couple of times, is that you can change the interval based on what you're plugging in. So I'm going to change my interval to thetas instead of x's. And then I don't have to go back to my x's at all. I can just plug the number into the problem at the end. Since I've already done the other method, I'm going to show you the second method so you can see how that works. They both work out to be the same way. It just depends on which one you feel is less work. These are x's, correct? Okay. So in the u sub method, you typically are plugging them in over here. We're replacing x. So I'm going to have my 0 equals 3 over 2 tangent of theta. So 0 equals tangent of theta. So what's theta equal? 0. Tangent of 0 gives you 0. The next one I'm going to have, so that's that bottom piece. I have 3 square root of 3 over 2 equals 3 over 2 tangent theta. That means I have the square root of 3 equals tangent theta. So theta equals what? Pi over 3, yeah. So the easiest way to, so you're, the vast majority of the time, I'm not even going to say 98% because depending on the numbers they give you, they're going to give you ones that work with the unit circle. Sines and cosines are really easy to find in the unit circle because they're the ones that are there. Tangent, you typically have to do a calculation for. The easiest way to remember this is pi over 4 is 1 for tangent. Okay? So if it's bigger than that, it's pi over 3. If it's less than that, it's pi over 6. Square root of 3 is bigger than 1, so therefore it's pi over 3. Okay? That's the easiest way to remember it, to get your number without having to do a ton of calculations. Okay? All right. We now have all this stuff to plug into this problem to translate it over to, like, we haven't even actually done the integral yet. We've just literally done a whole bunch of translation. So this becomes from 0 to pi over 3. The top becomes 3 over 2 tangent theta to the third over 27 secant to the third theta times 3 over 2 secant squared theta d theta. I'm going to rewrite it over here, actually. I'm just rewriting it.
It was pi over 3.
It was. $27. It was 3 over 2. And that was tangent, not secant. Yes. Okay. All right. So from 0 to pi over 3, I have 2 secants on top, 3 secants on the bottom, so I can cancel out 2 of those. So I have tangent to the third theta over secant theta d theta. That's the trig functions. So now I have 3 squared to the third times 3 squared over 27. So that's 81 over 16 over 27, right? Which comes out to be 3 over 16. So I could put the 3 over 16 in the front. It's, you flip it over, so it's 1 over 27. It's 81 over 16 divided by 27,
Oh.
which would be 81 over 16 times 1 over 27, which is how I get 3/16. I know it looks weird the way it's written. It's really easy to screw that up.
Those fractions are kind of neat.
Yep. Yep, they are.
Skip,
All right. So we're here now. What do we want to try now?
I would like to take the integral.
We still actually haven't done the integral.
And once we do that, we can just plug stuff.
Remember I said at the beginning, the problem isn't going to be the calculus, it's all the algebra. We've done all algebra so far. Yes. Yeah, let's change them to sine. Whenever you have the tangents and secants, it's always easier to change the sines and cosines. So I have, so this becomes, what do I have? Sine to the third theta over cosine to the third theta. And secant is 1 over cosine, so I have cosine on top. So 3/16, 0 to pi over 3 of sine to the third theta over cosine squared theta. D theta?
Yeah, that's right.
All right. What did we learn last class? That's not what we learned last class. I'm like, wait a second.
Going out.
Yeah, when we have the odd ones, we can pull things out and change things.
Yeah.
So we can change this to,
310.
we can change that to sine squared, which is 1 minus cosine squared theta over cosine squared theta. And then sine theta is left over. And now I can do u sub. So if I'm going to make u cosine, du is negative sine theta. And I also want to change those to u so I don't have to go back. So u of 0 is 1. And u of pi over 3 is 1/2.
So
Yes.
when we go into U substitution,
Wait.
we need to change the terms to U.
Yes. You don't have to. You can go back to the thetas if you wanted to, but you don't have to. So this is again, the same concept we did before. You can leave the units alone. You just have to then go back to them, or you can find the units.
Are you gonna plug cosine theta back into whatever U ends up being?
No, that's what I'm saying. That's why doing this, I don't have to do that now. I can literally leave it in terms of u and plug my problem back, plug the numbers into it. You'll see in 1 second. All right. I think that's actually wrong. Wait, no. Line. Square root of 3 over 2. Square root of 2 over 2. 1/2. 0. Yeah, I had it right. Like, it's always remembering, like, is square root of 3 over 2 bigger than 1/2? Or it's like, so it's like those little things. No, I have it backwards.
Or not?
Well, yeah, I do have to do that too. Hold on. I think that's not 1/2. Nope, it is 1/2. Okay.
Let's check that.
I have the answer.
Oh.
To be fair, everyone in here has the answer. These are the examples in the book. I have the book on my screen. So to be fair, you all have the answer to these. You don't have all the extra steps of my great amusing lectures in the book, but you do have the book. All right. So we're gonna go back in here. I have 3/16. I have 0, or that's not that 0. 1 to 1/2. I'm going to change my cosines. So I have 1 minus u squared over u squared. And this becomes a negative du.
Probably just plug everything in.
So I'm going to make 2 changes to this problem. The first one is, notice how 1/2 is smaller than 1.
Yeah.
We always like them the other direction. That swaps that. So I can now do 1/2 to 1 and get rid of the negative sign. Second thing I'm going to do is I'm going to split this up. Because the addition's on the top, I can split the bottom into 2 pieces. So I have u to the negative 2 minus 1 du. Yes.
Can you show how you got u to the negative 2 minus 1?
So 1 over u squared. That's the 1 over u squared, and then the u squared over u squared. So 1 over u squared
Yeah.
is u to the negative 1. U squared over u squared is 1.
Missed it, though. We went from what we had and just went into.
Hey, let's see, after like 5 slides, we now get to do integration.
I refuse to do it now.
So I have negative 1 over u minus u from 1/2 to 1. So 3/16. So I got negative 2 minus 1. Oh, sorry, that's the wrong one. Yeah, I did it backwards. Negative 1 minus 1 minus negative 2 minus 1. Negative 2 plus 3 is 3/16. Hold on.
You're telling me I could have stopped all my work after I got the 3/16 on the outside.
No, hold on. I see something wrong. Hold on a second. This script my sign somewhere. Oh wait, hold on. Wait. Oh, you know what I did? No, that's fine. Or did I switch something here? Hold on a second. 1 minus.
Is there a negative sign?
Yeah, that's where the negative du comes in.
No, I'm talking about at the end, right? We go all the way to the end.
I'm gonna go for
Where
it.
you took down the integration
Yeah, then just stay to the end.
at the last second. You plug in negative sign. And the negative sign.
I didn't plug in negative sign at all.
Gotta switch the U back, right?
No, no, because I changed my intervals. I changed my units. I don't see anything wrong with that. Is it -1/2?
Yeah. it is-
No, it's -1/1/2.
Yeah.
Oh, there, got it. Okay. Say, I knew something was off. So that's now 5/2. Yeah. So it's 3/16 times 1/2. That's better. I knew there was a mistake somewhere. I was literally trying to find it because I'm like, I knew the answer was off by that. I'm like, where? Because they didn't flip it, where we did. So I'm like, I had things backwards from what they had because they flipped this around. That was a mistake. Okay, so there you go. No, so the reason why we didn't have to go back to sign is I changed my unit. I changed my interval. So in the very beginning, we took our interval that was in terms of x's and we changed it to thetas. Then when we changed it to u, we changed those from thetas to u's. So this way, I didn't have to then plug back in the theta and then plug back in the x and then plug in the numbers. I did that step ahead of time, which saves you time in the long run. Okay. You can do that only with definite intervals. If it's not a definite interval, you can't do that because you're not changing anything there. You have to actually go backwards. So, but that's that.
So in the minute and a half, I went to the bathroom. You guys switch your slides.
Technically one. I copied it over and just finished it. Because I don't think you left. I think this was up here when you left. I think I was working through this part here. Yeah. So really, I only did one slide.
So maybe there was a time warp. How long I was.
I have a question.
Yes.
If we had stayed with the theta world,
Mhm.
would the answer,
The answer still would have been 3/32.
so like somewhere, somehow, the pies would cancel that?
Yeah, because if I'd switched, because you would have been doing like sine of pi over 3, which would have given you an actual number. So it would have ended up being the same basic fractions here. They still would have been the same fractions. This step should have looked pretty similar. All right. That's trig substitution. And I'd say that Tuesday's lesson is going to be way easier, but I can't. I can say that Thursday's lesson next week will be easier. And I can say that next Tuesday's lesson is the hardest one we're going to have in a while. So Tuesday's lesson is partial fractions. So Remember how to do systems of equations? I'm actually going to show you a way that you won't have to use them. Yeah, I'm going to show you a way that you won't actually have to use the systems of equations to do the problems.
So I did miss any-
Huh? No, we're not going to do matrices at all.
Fix the answer.
So
So what was wrong with our answer?
the 1/2 at the end, it was 1/2, not 1.
No.
Yes.
Are we gonna have a dedicated class? You,
Yes. Yeah. So I think, hold on, let me look at the syllabus real quick.
is that prior to or after you have out the?
Yeah. So I'll give you the breakdown. I just want to see the dates because I'll give you the specific dates. 20, yeah, 22nd. All right. So we're doing partial fractions on Tuesday. I'm going to switch out. We're not going to do improper integrals. We'll do that later. So we'll do section 7.5, which is putting everything together, basically. We'll go over that on Thursday. I will give you the review test next Thursday. Paper copy of the review test. So that'll be the actual thing you're going to study from. On the 20th, which it says review chapter 6 and 7, I will do that review test in class with you. Okay? So my suggestion would be after Thursday, work on that review test before you come to class on Tuesday. Because I'm going to go over it, answer any questions and everything else you have. Okay? While you're going through and doing the review test, if you have to look something up, that's what you put on your index card. Okay? My review test is pretty much identical to my actual test. I just change a number here and there. Okay? So like it'll be 4 sign instead of 9 sign, things like that. So the rules will be the same. Okay? The first test is always the hardest just because you don't really know what it is like. So people freak out. But if you do the review test and you come to class and review and ask questions, you should be fine. I will be here probably by 4 o'clock on the 22nd. So you can get here early and start your test as early as you want. You'll have from 4 o'clock till 7:30 to do it. So technically you have 3.5 hours to do your test. You should not need that long. Yes.
Are we allowed to take a break? In
Yeah, you can go to the bathroom. That's fine.
Okay.
Yeah. So you should not need 3.5 hours to do this test. The test should be able to be done if you show up at 5:30 and you leave by 7:15. Okay. The test should be able to be done in 1 hour and 45 minutes. I'm giving you longer in case you want it. Okay. It's 10 questions. And when you're done with the test, you're done. You can go. So if you get here early and you finish your test early, you can go. All right. Does that answer all your questions? Okay. Anything you want. It just has to be handwritten. And you can use both sides of a 3x5 or 4x6 index card. So
need to work inches.
if you can find a 3-foot by 5-foot index card that actually claims it is an index card, you could use it.
Is that a challenge?
I want to see the package that says index card.
Okay. Okay.
Half poster board.
Amazon.